what I hope is what is an interesting and insightful conversation. So yeah, I'd like to tell you today and explain a little bit what is the high luminosity LHC project, which you probably, some of you at least, will have heard about. I'd like to highlight, as part of this conversation, some of the technological challenges of this project, and also discuss specifically in more details a subset of Canadian contributions, some of which that I'm most familiar with working on those projects. This is my outline, actually, that I just told you about, and that the roadmap we'll be following today. So just to set the stage, the Large Hadron Collider, or LHC, is the largest and most powerful collider currently operating in the world. It has a circumference, as you see here, of 27 kilometers, and it's located just outside Geneva. For those of you who've been to Geneva, you see downtown Geneva, Lac Léman, and Chamonix and the Mont Blanc in the background. So this collider actually accelerates protons and makes them to collide at a few interaction points around this ring at an energy of 13 tera electron volts, or TeV. Now, this is a timeline. The LHC started actually operation way back in 2011 at a center of mass energy of 7 TeV. It has since increased both its center mass energy, but also the intensity of its accelerated beam. We are currently, I guess, here where the red arrow sits, and we're at a point where we're right now, as we speak, recommissioning both the accelerator and detectors in preparation for what's called the LHC Run 3 data taking period. And this is actually physics collision are about to start in July. And the LHC program will actually complete relatively soon at the end of 2025. Now, I thought it may be fun to put a bit the technological capabilities of the LHC in perspective. So here's what you see here is a comparison of the LHC with other past colliders in terms of three key parameters: the type of particle being accelerated, that show up here in different colors. So the heavier protons are actually can be more easily accelerated, and you see that at the higher energy being achieved. And they're more easily accelerated to high energy, especially in a circular machine, because they don't lose as much energy by synchrotron radiation as electrons do. The collision energy achieved, most of you will have given, probably your undergrad students, the classic problem of calculating the energy available if you do a head-on collision versus a fixed target type collision. So of course, one advantage of a collider is that the energy of the two beams actually is available to produce new particle, as opposed to a fixed target experiment, where a significant fraction of the energy is actually used or expended in giving momentum to the outgoing particles. And then the other key parameter is the intensity of the accelerated beam, which is characterized by the instantaneous luminosity. That is the number of potential collisions per unit area per second at a given interaction region. So if you'd like to know, and I put the little formula here, if you'd like to know, for example, the rate of production of a specific physics interaction you're interested in, say the production of Higgs boson, then you just multiply the cross section for your physics reaction by the luminosity of the collider. So as you can see here on this plot, the LHC is quite a unique machine. It sits on the top right of that plot, capable of delivering collisions not only at high center mass energy, but also at very high luminosity or beam intensity, making it possible to acquire a vast amount of data, which allows us then to study extremely rare physics phenomena. In fact, the LHC has an extremely prolific and diverse physics program. I just wanted to flash this slide focusing, for example, only on physics output from the Atlas International Collaboration. We're talking about more than 1,000 papers that have been published to date on a variety of topics, from searches for new physics phenomena to studies of the Higgs boson, properties and other physics reaction predicted to exist in a standard model. So with this plot here, really, I just wanted to give you a bit of a sense of the physics reach of the LHC data set that it provides. So what you see here is a few examples of cross-section measurements for different physics reactions. And it really shows the extent of the reach of the current data set well into being able to study very rare phenomena with cross-sections at the level of down here at the level of femtobarns. Now, I thought, given the audience, that it may be fun actually today to compare these cross-section with those that many of you will be more familiar with, namely the lowest limit on the WIMP nucleon scattering cross-section. So of course, these are different things. We're a bit comparing apples and oranges, but just I thought it'd be fun just in terms of pure cross-section number to set the scale. So basically, I've put those two plots side by side, and you see that the rarest reaction that we're right now able to measure at the LHC are essentially 6 orders of magnitude higher than the lowest values of cross-section of rare events that are set in the WIMP nucleon scattering cross-section. And just quickly, just one more slide to give you again a sense of the physics reach of the LHC data set and where we stand. So this is 2 other example plot, and on the left here you see being shown here cross-section measurement again for different reaction, but that are compared, essentially data over theory, compared to our current best theory predictions. So while the current LHC data sample does make it possible to observe for the first time extremely rare reaction, for example, the production of 3 gauge bosons simultaneously. These extremely rare reaction, which we're interested in to further our understanding of the subatomic world, the precision of many of these measurements is statistically dominated. And you can see that with the different color, shaded color of red and green. On the right here, you see a plot of the Higgs boson cross-section, production cross-section, so different ways of producing Higgs boson. And what I want to show here is that essentially these cross-section are measured at best at the 20 to 40% uncertainty level. So it leaves plenty of space for new physics phenomena in there to be hiding that we haven't seen yet. So the main message here is there's a large region of phase space that to date, even with the LHC data, remains unexplored. And really, it's a region of phase space that is within our reach with a significant increase in the size of our data set. So this is where the high luminosity LHC project comes in, because since the statistical significance of any measurement improves as the square root of the number of events, it's clear that after the end of the LHC run 3 that we're just about to begin, essentially the statistical gain that you would have in just running the LHC without a significant luminosity increase, really that gain becomes marginal. So the goal of the high luminosity LHC project is to significantly increase the LHC beam intensity in order to increase the available data set by, say, more than a factor of 5, which then in turn gives you an increase in statistical reach by more than a factor of 2. So this, what are we going to do? Well, this will allow us to significantly extend the reach of the LHC physics program, where we're going to focus on pursuing the exploration of the electroweak symmetry breaking mechanism in the standard model and search for new physics in really new region of phase space, meaning really rare processes or even challenging experimental signature that have not been fully pursued. So in a nutshell, the high luminosity LHC is a project that consists in major upgrades to both the LHC and all the ancillary infrastructure to achieve the following design targets. So the center of mass energy will remain more or less the same as the LHC, but we will achieve an approximately 7-fold increase in beam intensity, which will be achieved in part using, for the first time at the proton collider, a technique called luminosity leveling. This will, at the end of the day, after about 10 years of data taking, bring us and give us a data set that is about 7 times larger than the final LHC data set at the end of 2025. And then I will note that high luminosity LHC operation is scheduled to begin in 2029. So now to understand, then I'd like to dig a little bit deeper into how we can achieve actually higher luminosity. And this equation just shows the instantaneous luminosity of a collider, which is related, for example, to the bunch crossing frequency. At the LHC, it's 40 megahertz. Then the number of particle bunches that make up a beam. The higher number of bunches, the higher the luminosity. The number of protons per each of these bunch, and the whole thing is inversely proportional to the transverse size of the colliding particle bunches. So smaller sizes, you get higher luminosity. So to increase the luminosity, these are, essentially the few parameters with which you can play. Now, the bunch crossing frequency is actually set by the RF structure of the machine, and this is something that will not change at the high Lumi LHC. It will remain the 40 megahertz that we've been using at the LHC, which corresponds to a bunch separation of 25 nanoseconds. The number of bunches per beam at the high Lumi LHC will also remain more or less the same due to the complexity of the beam dynamics. So typically the LHC is filled with about 2,800 bunches, thereabout. And it's really the complexity of the beam dynamics and the instabilities that start showing up due to collective effects when you put in a larger number of particle bunches. Now, having said that, however, the one parameter that will be changed at the high luminosity LHC is the transverse size of the colliding bunches. So to make a smaller beam size, the trick at the interaction region, the trick is to use a stronger focusing magnet close to the interaction region. And for this purpose, an innovative new wide aperture quadruplet magnets. You see a picture here. They've been designed based on a novel use of niobium tin superconductor to provide now a much improved greater field of 12 Tesla. To increase the instantaneous luminosity, also you can play with essentially putting more protons, packing more protons into a bunch. At the LHC, each bunch currently contains approximately 10 to the 11 protons per bunch. And the goal at the high Lumi LHC is to nearly double the bunch population. Now, to achieve this, actually required a significant refurbishing and upgrade to the LHC accelerator and injector chain. So there are multiple stages of acceleration before you get to inject into the LHC. And this included actually a completely brand new LINAC that you can see here. But increasing the bunch population comes actually with a significant technological challenge. It turns out that with a higher bunch population, you need to have a larger crossing angle of the beam in order to minimize and keep under control any beam effects. And this larger crossing angle, unfortunately, comes at the cost of lower luminosity. So it goes in the wrong direction because you're actually with a large angle, you reduce the overlap between the bunches. And you can see that on this picture here at the bottom. So to compensate for this effect, there's new high frequency RF transverse deflectors that are called crab cavities. which will be added around each interaction region in order to really just locally around that interaction region, rotate the proton bunches. So you just kick the proton bunches in such a way as to maximize their overlap when they cross. And again, this is illustrated on this schematic diagram where you maximize the area, this purple area of interaction. Now, one of Canada's contribution to the high luminosity infrastructure is actually in delivering parts of these components. So I'd like to give a bit more detail on this contribution. This Canadian contribution actually was formalized in 2018 when Canadian Minister of Science, Kirsty Duncan, announced a $10 million support from the government for trying to build 5 high luminosity crab cavity cryogenic module. And this is really a natural way that Canada can contribute, which builds directly on Triumph world-renowned expertise in cryogenics. So Triumph will lead, as I said, the production of these cryo module with a $2 million in-kind contribution. So in total, we're talking about a $12 million project, which will serve actually as essentially the Canadian buy-in into the high luminosity LHC program. So allowing Canadian scientists like me to access the future unique data set that will be produced. So you can see here actually a schematic diagram on the right of a crab cavity cryo module containing here 2 RF dipoles. And what will be done is essentially qualified crab cavity. So these RF dipole module will be delivered to CERN and will come from the US. Then Triumph will assemble the cavities into these cryo module, qualify them, and ship them the whole module to CERN. So we have a plan for how to achieve higher luminosity, but this higher luminosity actually imposes unique challenges to the detectors, such as ATLAS, these detectors that are used to record the results of proton-proton collision. So in particular, at high Lumi LHC, up to 200 simultaneous collision will occur at each bunch crossing produced. So every 25 nanoseconds, we have pileups of up to 200 collision. So this produces a very high flux of particle traveling through the detector. And in particular, the detector components closest to the interaction region actually will be exposed to a very high level of radiation of order 10 to the 16 neutron equivalent per centimeter square. And over time, a total integrated dose of 10 megagray over the lifetime of the project. So, and to give you an idea, this is a picture here actually that shows an event display from a simulated pileup condition that will exist at high Lumi LHC. So ultimately, we need to be able to tease out of this mess the one information about the one collision. For example, you see here in blue, the one interesting high momentum transfer collision from this large background. To achieve this, to achieve the required performance, detector performance to do this physics program at high Lumi actually required major upgrades to the ATLAS experiment, and these are underway over time. Essentially, every ATLAS detector subsystem is having major work done, which is summarized in this table, going from inside the detector to outward. Canada is contributing to several of these upgrade projects, and given the limited amount of time I have today, I'd like to just give you more details on and focus on 2 of the Canadian upgrade project that I work on, namely the installation of a new muon detector system in the forward region and the development of a completely brand new readout electronics for liquid argon calorimeter system. So let me first present the actually the new muon small wheel project and the particular contribution to this major upgrade project. So this is a schematic diagram of the Atlas detector. Again, maybe highlighting that these little people here are actually normal-sized human beings to give you the scale of the Atlas detector. What we're talking about is actually completely replacing the wheels that you appear now in blue, which we call them our small wheels. But small is relative. They're about 12 meter in diameter. This is as opposed to the big wheels, which you see in the background. So the idea is that we have designed and built new muon small wheels to replace existing ones. So this is a picture actually of one of the new muon small wheels that went in recently into and it has been recently integrated into Atlas. Here's a schematic diagram actually of a quarter of the Atlas detector. So the interaction region, the proton collision occur here at the bottom left, and you see essentially 1/4 of the Atlas detector. So up to now, actually a large fraction of hits identified as muon candidates in the forward region of Atlas by the trigger system are in fact fake muon signals. And fake signals arise essentially arising from other sources, either non-muon particle or muons, but not coming from the interaction region. And these fake signals really include, cavern backgrounds, and as I said, muon produced in the halo of the LHC proton beams, etc. And this effect, actually, this kind of background will be increasing significantly with larger luminosity. So without modification to the detector, our fake muon trigger rates in the end cap would become completely unsustainable and completely saturate our trigger bandwidth at the high lumi LHC, which I mean would require us to, I suppose, just increase the transverse momentum threshold of our trigger to a level where we wouldn't be able to do physics. So Atlas decided to replace the original muon small wheel, as I said. This is this gray area here with the new detector system. And it's a new detector system that has a new capability, which is to reconstruct muon track segments locally, so here locally, with a resolution of 1 milliradian, such that we can actually reconstruct this direction, a little track segment, both at the trigger level and in the offline reconstruction. So with this capability, then we'll be able to maintain in the NCAP region muon triggers of low transverse momentum for the physics we want to do, even at the ultimate high lumi LHC luminosity. So the idea of how we significantly reduce this fake background is illustrated here on this diagram, where you can see that with the knowledge, if you have the knowledge of a track segment in the new small wheel, you can match that information to a track segment reconstructed in the big wheel, and then you can clearly see if these track segment points towards the interaction region or not, allowing you to then reconstruct real muons coming from the interaction region with a high purity. And this is shown here. This is the expected improvement in the fake rejection. So what you see here is the pseudo rapidity distribution, or if you wish, it's proportional to the polar angle. So the NCAP region is on the left and on the right. The middle part is the barrel section of the Atlas detector. So what you're seeing are the number of muon candidates passing the trigger from real run-through data. And it shows the region expected to be rejected using the new small wheel in run 3 in orange. So everything that is in, I guess, yellowish orange, light orange here on the left will actually go away with the use of the new small wheel. And then resulting ultimately in having almost all the triggered muons, which are the blue histogram, being what we call good or real muons, as shown in red. So overall, the new small wheel and the use of the new small wheel will reduce the forward muon trigger fake by a factor of about 7, so almost an order of magnitude. So it's really a case of, it's not just necessary, it's a case of survival if we want to do physics at high luminosity LHC. Now, the new small wheel is made of two different technologies that can satisfy the performance requirements independently at both the trigger level and the offline reconstructed level, so providing full redundancy. The wheel is made up of these wedges that you see here. Hopefully you see my pointer. And each wedge is actually a sandwich of two different detector technology. In pink are what we call small strip thin gap chambers, and in the green are micromegas. In total, we have 8 layers of small strip thin gap chambers and 8 layers of micromegas, so for full redundancy. And Canada actually built a quarter of all the so-called STGC chambers, so the pink part, and that's what I'll focus on the next few slides on this technology. So what is an STGC? It's really just a multi-wire gas ionization chamber, but it has the unique characteristic that the wire to cathode here distance is actually smaller than the wire to wire distance. Each STGC has actually 3 different readout paths. So ionization signals can be read out or are read out directly on the wires, and they're also read out on capacitively coupled copper electrodes on each cathode board. So as you see here on the top, one of the cathode board actually has large copper pads about the size of a big hand, and these copper pads, the information from these copper pads are used for triggering purposes. And on the other cathode, we have small copper strips of 3.2 millimeter wide that are used for precisely reconstructing the position of the muon. So STGC really consists, as I said, a thin gas type volume that is immersed in an electric field. The electric field is created by applying a high voltage on these 50 micron diameter wires. We typically run the STGC with about 3 kilovolts as a high voltage value. So this produces within this geometry, you can see here the electric field line such that the highest electric field is actually closest to each of the wires. The principle of operation, I mean, most of you will be familiar with ionization detector. You have a charged particle such as a muon traversing the detector volume. As it goes through the gas, it ionizes the gas, producing charge carriers. These charge carriers then either the positive ion or the negative electron will drift in the following the electric field line, and it's the motion of these charge carriers that produces an electric current on the electrodes that can be read out. We use a mixture of a gas mixture of CO2 and N-pentane, which it has it's a highly quenching gas mixture, which makes it possible essentially to operate, as I said, at a very high voltage of 3 kilovolts, which gives us a gain. So for every ionization event, we essentially multiply that by 10 to the 5. So these chambers have a relatively high gain, and you can literally just plug your scope into it and directly into an electrode and see it. So you don't need like super mega sensitive electronics to read it. You just can see it by eye, a signal on the scope. So these given the high voltage that we apply, we operate these ionization chambers essentially in the quasi-saturated mode. So we don't have any energy resolution, but these are turned out to be operated in this way, highly efficient detector that provides very fast response because it's very thin and provides a very large signal amplitude. So I'll just go through some of these really unique characteristics of these STGC that clearly match our needs for the required detector subsystem performance. So as I said, they're highly efficient detectors. So what you're seeing is the muon hit efficiency as a function in XY position. So over the surface of these detectors, it's essentially 100% efficient. The lines you see horizontal are actually support structure just to support and maintain a completely uniform size of a gap. So this is just less sensitive areas. These chambers have an extremely fast response because of the very small gas gap and a high electric field around the wires, and also a small wire-to-wire distance that ensure good timing properties. So as you can see here, this is a histogram of number of entries as a function of time. 95% of minimum ionizing particle signal or muon signals are collected within actually a 25 nanosecond time window, which is essentially what is required for us to be able to do a bunch crossing identification timestamp at the LHC. We can achieve, relatively speaking, excellent spatial resolution. We're not talking about a handful of micron resolution, but remember, we're trying to cover an extremely large surface area. So we can achieve down to, in perfect condition, down to about 50 micron spatial resolution by putting together the signal from neighboring strips. They have a very high rate capability, again, in part because of the very high field. So your charge carriers move very quickly, and they're able to sustain a very high particle flux. This is shown, for example, in this plot of rate of photon irradiation on the x-axis versus something that is proportional to the gain of the chamber. And you can see that we can operate each chamber all the way to about 20, essentially a flux of 20 kilohertz per centimeter square. This is really high, while still retaining high efficiency for identifying muons or minimum ionizing particle. They're intrinsically quite radiation hard in that studies have been done and show no deterioration up to total irradiation of 6 coulomb per centimeter square. What you're seeing here is that most of the radiation damage actually comes from these various radical sticking to the little gold, thin gold wires as a function of time and deteriorating essentially the quality of the electric field, and in the worst case, even potentially starting some discharges over time. In Canada, so as I said, Canada successfully built and delivered a quarter of all the STCC chambers necessary to build the new small wheels. In addition to actually significantly contributing to the construction of the wedges you were looking at and the overall building and commissioning of the new small wheel at CERN. So we had a big Canadian contingent, and still have actually working on that. Wheels, the status of this project is that the 2 new small wheels were actually installed last summer, and the current status is that there's a lot of intense commissioning work that is ongoing to finalize the full integration, in particular of the full readout and calibration chain into the whole Atlas DAC system in preparation for the Run 3 that will soon start in July. So I just wanted to then move on to the second upgrade project that I wanted to talk to you about, which is essentially the design of a new readout electronics for the liquid argon calorimeter. And this is a slide introducing the liquid argon calorimeter system in Atlas, which is located outside actually the solenoid. It comprises an electromagnetic part, both in the barrel and end cap region, and a hadronic end cap subsystem, as well as a distinct forward calorimeter together covering essentially almost down to a pseudo rapidity of 4.9. Now, Canada has built actually a significant fraction of both the HEC here and the FCAL that you see at the middle there. Now, this detector, it turns out the liquid argon technology is in itself radiation hard. So the calorimeter will operate reliably during high luminosity LHC data taking, so that's not a problem. However, the radiation dose will surpass the level for which the existing readout electronics was qualified for originally, like way back in the 80s. Furthermore, the existing readout is actually incompatible with the needs of the trigger upgrade, which is required to remain sensitive to physics at the electrowave scale. So as a result, the entire readout electronics is being scrapped for this system and needs to be replaced. And this is a great opportunity because, I mean, the whole readout was actually designed and built, as I said, in the 80s. So now we can take advantage of recent innovations in microelectronics, high-speed communication, and actually leading-edge FPGA technologies. So unlike the existing readout, what we're developing, the new electronic readout will be based on a completely free running architecture where essentially all the data are continuously digitized by new on-detector electronics and sent off detector for further processing, but in terms of digital signal processing. Here, the main design challenge for this upgrade is to essentially digitize the data as early as possible in a very high radiation environment, and then to deliver the information to the new trigger processor as quickly and accurately as possible. And the information we want to deliver is essentially the energy that was deposited in the different section of the calorimeter. So the next slide, I understand, is way too detailed. I'm not going to go through this. So, but I just want to, it's a schematic diagram of the plan upgrade with different components. But I just wanted to highlight the main component of the readout that consists of a new on-detector front-end board. So this is the analog parts. And then a new off-detector digital signal processor system. And Canada is contributing to the development of both of these components, the on-detector and off-detector component. Just to say a little bit more, the new front-end board are designed to essentially amplify the incoming signals from the liquid argon. It shapes the signal and then using a bipolar filter, and then it performed a digitization at a sampling rate of 40 megahertz, and then transmit all this information to the off-detector digital signal processing system. And this new digital signal processing system is responsible for, as I said earlier, reconstructing the energy, but also time of arrival of the liquid argon signal. And it provides input to the trigger system. It buffers data until a trigger decision, and then it sends all the data to the data acquisition system. Here's actually a plot showing what a raw signal from the liquid argon electrodes looks like. It's actually a triangular pulse of 450 nanoseconds long. This is, remember, much longer, and this is one of our challenges. This is much longer time signal than the bunch crossing rate, which is 25 nanoseconds. So I'll be talking about the piling up of these signals one on top of each other in a minute. Now, this raw signal is, as I said, shaped by a CR-RC square filter into a bipolar signal, which you see the shape here. And the reason we use this bipolar signal is that helps reduce sensitivity to pileup noise, and I'll say a bit more about that in a moment. Now, the amplitude of the signal here is proportional to the amount of energy deposited in the LAR. And well, I mean, by design, the time integral of this bipolar pulse shape is actually 0, which has the advantage of ensuring that the baseline of the calorimeter signal does not shift as a function of time with the presence of pileup. So I'm going to show you here, and I wanted to, talking about pileup, explain to you a little bit more what we mean by both in time and out of time pileup. What you see here are distribution. So the x-axis is essentially time in chunks of, these are bunch crossing numbers. So there are 25 nanosecond samples. So samples taken at 25 nanoseconds. On the vertical axis is just ADC count, essentially. And what is shown on the left is the effect of in-time pileup. So what is in-time pileup? It's the fact that when you have essentially two bunches crossing, so one bunch crossing, you can have multiple proton-proton interaction in the same bunch crossing, but depositing energy in some of your in calorimeter readout channel. Now, the impact of in-time pileup is to produce essentially a larger amount of ionization in the detector, which then you reconstruct as corresponding to a slightly higher amount of energy than the energy that was deposited from the physics signal that you were interested in. Out of time pileup, on the other hand, it means that given, as I said, the length of the liquid argon pulse, which spans several bunch crossing, if the, sometimes actually quite often you'll have, say, energy deposited in a readout channel less than 450 nanoseconds before or after a signal of interest. So the two time-shifted pulse shape essentially will overlap in time, which results in a distortion of the signal pulse shape. Because ultimately, you're trying to, in digital signal processing, assess as best as you can the height of this pulse in order to reconstruct the energy that was deposited. But then you have this pileup, out-of-time pileup on top of that. So the analog shaping is an important step to reduce the total noise, and you can see actually the impact. And one thing you can play with is the peaking time in your analog filter. So a longer pulse shape is preferred to reduce the electronics noise, but on the other hand, the narrow pulse shape is better against the pileup noise. This is shown on this plot on the right. So different, so you actually optimize, and we've done the studies to optimize it, a peaking time that is roughly compatible with what we need in a large part of the calorimeter, but we will be designing the analog part to have a programmable peaking time to adjust for differences in the signal in different parts of the calorimeter. Then on the digital filtering side, right now we're actually exploring what will be the most, what will give us the best performance in terms of energy resolution from different digital filtering. Right now, what is currently used is called optimal filtering. It's essentially a linear combination of digitized pulse samples that is designed to minimize essentially the mean square of the total noise. So it works well, but not against out-of-time pileup. So they are, we're also looking into machine learning type method based on ANN, CNN, and RNNs. And you can see, take a little glimpse at, compared to the optimal filtering here, how we improve slightly. We're able to, certainly it looks promising. Some of the performance of these machine learning methods look promising, but the challenge is really the implementation in FPGA. So in the past few slides, I just provided you with some details on two of many ongoing upgrades to the Atlas detector. And I would just like to end this seminar by providing a bit of an idea of what these improvements will allow us to do. So some of the physics prospects include what we'd like to do is determine the determination of the Higgs boson properties. And in particular, we should have enough data to essentially measure the Higgs coupling at the percent level, no longer 20 or 40% level, but at the percent level. And we expect to have sensitivity for the very first time to be able to measure the trilinear self-coupling. So essentially think of 3 Higgs boson interacting with each other. And the measurement of this coupling is directly linked to the shape of the famous Higgs boson Mexican hat that described the shape of the Higgs boson. So this will allow us to really confirm, like, is the Higgs field really follow the Mexican hat shape, for example. We will be doing precision measurement, of course, of known standard model processes, and I'll show you one example next slide, and search for new physics. And for example, even though we're not increasing the center of mass energy, our mass reach for heavy resonance will be extended by about 20% at high lumi LHC. And we'll certainly have increased sensitivity in searches for rare processes such as electroweak SUSY. So I will just end. I have two last, I think, slides. Just sharing a little bit of my current passion. So I'm particularly interested in studying the interaction between gauge bosons, and the reason is that within the standard model, so the standard model is quantum field theory based on this particular gauge symmetry group, and essentially this non-abelian gauge symmetry completely determined, there's no wiggle room, it completely tells you and determine what these gauge boson interaction should be. So what is the coupling strength as well as the type of coupling. So the form and the strength of all the boson self interaction are fully specified in the standard model. So the idea is you make a measurement in real life, and then you compare with your theory that has absolutely no free parameters to search for potential hints of new physics. And one of these multi-boson interaction I'm interested in is one that involves W bosons and 2 photons, like you see here. So these are really, really rare, and we're actually working really hard and looking forward over the maybe before the end of the year, being able to publish a first observation of this very, very rare events, type of events, whereby you would have the production in your detector of a W and 2 photons. Again, that will proceed through this quartic gauge coupling. So if we can observe for the first time this type of reaction, then we can turn around and also study these interactions, and if not seeing new hints of new physics, certainly we can set constraint on potential anomalous quartic gauge coupling that could arise in nature. So that brings me actually to my summary. The high luminosity LHC project, as I said, hopefully convinced you, will significantly extend the reach of the current LHC physics program. There are major upgrades both on the LHC side, but also on the detector side going on as we speak. And many of those projects have significant Canadian contribution that I was not able to give justice to in the seminar today. But I tried to focus on at least just a couple to give you a little bit of the flavor of what is going on in Canada, but also some of the technological challenges that we are facing and how we're solving these and addressing these challenges. So we're looking forward to exciting new physics opportunities for the coming several years. So I think I'll stop here at this point in time. Thank you for your attention.